So for our first unit of the second semester, we're going to leave triangles behind for just a little bit and kind of expand our shapes and go beyond three sides and start dealing with four sides, kind of four sides and up. We do have to cover some basic vocab, which we're going to do in this first slide, then introduce some pretty straightforward properties that apply to all polygons. Then we're going to start focusing on particular quadrilaterals and the properties that they have in subsequent lectures. Right? So what we have here, there on the screen there, that five-sided figure is a polygon. Polygon is not the story of somebody's lost bird, but it's a two-dimensional closed plane figure formed by segments connected endpoint to endpoint. So every part of that is important, right? Two-dimensional. You could sketch it on a piece of paper and it would be just as is. It's a closed plane figure. There's no open areas to get kind of, there's a clearly defined interior and exterior formed by segments, straight lines. We're not talking about curves. A circle is not a polygon. And connected endpoint to endpoint. We're not talking about when we were looking at our triangle conjecture problems and we had those kind of bow tie looking things where we had two lines crossing over and forming the triangles that way. Those shapes in their entirety would not be a polygon because they're formed by segments not connected endpoint to endpoint. So what we have here is a polygon. Meets all those criteria. Vertices are just the point at which the two sides meet. The vertices are how we name the polygon. So this would be polygon A, B, C, D, E. We don't usually go too crazy naming things much beyond a pentagon like we have here. But however you name them, you have to name them in order. You can do it alphabetically here, starting at A. You can go backwards in reverse alphabetical order. What you can't do is name this one A, C, E, B, D. That wouldn't work. You have to kind of go either clockwise or counterclockwise to name the polygon. But you name them using the vertices, not unlike we did with triangles. Triangles are polygons, so it should stand to reason. When we're talking about what diagonals are, right, we're talking about a segment that connects vertices that aren't connected by sides. So if I put these segments in here, EC, DB, AD, and so forth, right? These are going to be, I don't like this feature. These are going to be diagonals. Now what's important to note, right? What makes them diagonals is what they are connecting. They're connecting vertices that aren't connected by a side. AB is a side. It can't be a diagonal. And AC is a diagonal because it's not a side, but it's connecting two vertices. A diagonal does not have to go diagonally. Sometimes people think that because it's going diagonally, it's a diagonal. No, a diagonal can go straight up and down or vertically or horizontally. It doesn't have to be going kind of, okay, I'm not going to mess with that anymore. But a diagonal connects vertices that are not otherwise connected by a side. Convex is any polygon whose diagonals all lie within the figure. This pentagon here is convex because all the diagonals lie within the figure. There are no diagonals that go outside the figure. I'll sketch a simple one right here that isn't convex. Right? If you take another pentagon here and say, all right, well, I've got this one here, which more or less is a polygon. It's not very well drawn, but that's another pentagon. But I can take this one and say, oh, there's a diagonal because these two vertices here are not connected by sides. That's a diagonal. That's on the exterior of the shape. that makes it concave, right? So convex is all the polygon, all the diagonals lie within the polygon. Concave is there is a diagonal on the outside of the shape. I like to think of it, if you need a better way to remember it, for me, it helps to think a concave polygon is caved in somewhere, it's dented, and that's what you have there, concave. Right. We might have talked about this definition before, but as we look at kind of the stop sign shape here, the octagon, this is a regular polygon. And what regular means is it's both equilateral, as marked here by the sides, and equiangular. So we know that all the sides are the same length and all the angles are the same length. Okay. And you have to be told that. You have to be either told that it's a regular polygon, or it's you have enough information like you do here to work under that assumption. Okay, so that's what regular is. We've talked a little bit about that when we talked about equilateral triangles that are also equiangular. That's right. That's just another word for regular. It's easier to say regular than equiangular and equilateral. And then how we classify polygons are by the number of sides. And these are kind of this list here is pretty much the ones that I reserve the right to have you know. If we're talking about, I'm going to use any of those and not provide, like in parentheses, heptagon in parentheses 7. Those are the ones that I would expect you to know. There's not really all that many of them. You know triangle, you know quadrilateral. Most people know pentagon. Most people know octagon and decagon. So there really aren't that many to remember. But if, for instance, I was saying, okay, a 57-sided figure, there is a Greek prefix for 57. I have no idea what it is, nor do I want to know. I'm just going to call it a 57-gon, or a 31-gon, or so on and so forth, whatever it might be, right? So if you see anything like that, that's just telling you it's a polygon with that many shapes. Anything that ends in gon is some sort of two-dimensional figure, right? Now the first of, I think, just 2 conjectures here. We've got our octagon here. We've got our 8-sided polygon broken up into 6 triangles. So these triangles are all formed by the diagonals that are coming out of one vertex, right? And each of these has 180 degrees in them. Because we know that about triangles. And we also can probably extend that idea to say, well, I know that a square is just 2 triangles that share the 2 right isosceles triangles that share a hypotenuse, so stands to reason that a 4-sided figure is probably going to have 360 total degrees. Well, we can extend that thinking to really anything, that any number of sides, if it's a convex polygon, by breaking it into triangles. So the Polygon Sum conjecture allows us to say, okay, so if we want the sum of the angles added all, in the same way that it's nice to know that all the angles in a triangle add up to 180, we can do that for any number of sides simply by using this pretty straightforward formula here, which is n, which is the number of sides, minus 2 times 180. Now, because of that, you can also say, you could write it as 180 times n minus 360 if you want to distribute. Most people like this way here. I think both of these versions are on your formula sheet. So if you wanted to, if you had some reason to find what the measure of a 57-gon would, all the angles in a 57-gon add up to, we can say, well, n is 57. So I'm going to take that formula there, easy enough to show what you do. And that's all you have to show me right there. You're going to do it in the calculator. You're going to do 55 times 180, and you're going to get 9,900, right? I can't I cannot envision why you would want to know what all the angles of a 57 gon would add up to, but it's nice to know that you can apply something to get an answer to something here, right? But knowing what something adds up to, that's kind of one of our problems, right? What's kind of one of our, most of the problems that we talk about are going to be that type of thing, which is to say, they either are equal to each other or they add up to something. And if we had that, we know what we can do to solve for a missing value. Okay? And then lastly, but not leastly, if I tell you that this here is a regular triangle, you know that all the angles are 60. Right? So I want to look at the measures of angles 1, 2, and 3. Now, the measures of angles 1, 2, and 3 are exterior angles. They're supplements of the interior angles. Or they're the other half of a linear pair with the interior angles. Right? So if I know that this is a regular triangle, each of the interior angles is going to be 60. Each of the exterior angles is going to be 120. And if I add up all of those, I get 120 plus 120 plus 120. That gives me a total of 360. Right? I take this rectangle here that has 4 90-degree angles. I know that these are 90 out here. These exterior angles are 90 out here. And I add up those exterior angles, those 4 exterior angles, and 4 90s gives me, hey, how about that? 360. That's one of those always situations, right? It's called the exterior angle theorem. The sum of the exterior angles of a convex polygon always measures up to 360 degrees. Right? So those are our Polygon Basics and a couple of Polygon Sum conjectures. Neither of them are all that complex. Not a lot of work to show, but there's include those theorems by name to explain how you got there. We're going to get plenty of practice with both this and the next lecture, the next time we meet, whenever that might be. So please let me know if you have any questions about this stuff. I hope this helped.